So we got 5.4. This section covers the fundamental theorem of algebra. So some properties of roots of polynomials, polynomial equations. Okay. So these two bullets are properties of roots of polynomial equations. Now, if a polynomial equation is of degree n, okay, so degree n, then counting multiple roots separately, then the equation has, oh, what is going on here? I haven't seen this before. How do I undo that? Go away. Okay, sorry about that. Then counting the multiple roots separately, the equation has n roots. N roots. All right? So if a plus bi is a root of a polynomial equation with real coefficients, then the imaginary number a minus bi is also a root. So if I know that a plus bi is a root, then I get a minus bi for free. This is something special in math called the conjugate pair. The conjugate pair always occurs for complex roots. So for example, if I knew that like 2 plus 3i was a root, imaginary root, then I also know that x equals 2 minus 3i is another root for that particular polynomial equation. Okay, so if I know one of them, I can get the other for free. Okay, same thing if it was like, x equals, maybe it was like 4i. Okay, then I know I have x equals negative 4i is my other solution. You think about 4i written in the form a plus bi. 4i would be equal to 0 plus 4i. Then the conjugate pair would be 0 minus 4i. That's where that negative 4i came from. Okay, just wanted to make sure we're on the same page. Now, the fundamental theorem of algebra guarantees at least one root for a degree 1 or greater. This allows us to apply the linear factors theorem. Very powerful theorem that says I can take any f of x, degree n, so an x to the n plus an minus 1 x to the n minus 1 plus blah, 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 all the way down to a1 x to the 1 plus a0, that typical one. So this is just a degree in polynomial, okay? This can be factored into n linear factors. Now, they may not be distinct, but there are n linear factors. So what is this going to be looking like? F of x becomes some number multiplied by x minus a number times x minus another number times x minus another number, however many factors I have. So for this one, I have I have n of them, so I put an n down here. Okay, 1, 2, 3, dots, all the way to n. N could be 17, it can be whatever it is. Okay, and then this c, these c's could be complex numbers. They could be real numbers. They could be rational. They could be integers, natural numbers, so on. Okay, so basically just think of those c's as any number you can think of. all right, any number that you know. All right, you want to learn numbers that are outside the complex field. You're going to need to go to graduate school, and they'll tell you about quaternions. All right, so good luck with that. All right, so here's your example. Find a fourth degree polynomial function f of x with real coefficients that has -2, 2, and I as zeros, and we know f of 3 is equal to -150. Okay, so this is a typical example that you might run into where you're just asked to construct a polynomial that satisfies these characteristics. So how do we do this? All right, what characteristics are important? Well, it's a fourth degree, so that means that ultimately I'm going to have some x to the fourth going on, right? With maybe some number in front, okay? But what do I know? Every function can be factored into this form right here, okay? So how many factors am I going to have? Well, if it's a fourth degree, I'm going to have 4 factors. So I know right off the bat, it's going to be some number times x, and then x, and then x, and how many are there? There's 4 of them. So I've got another x here. My job is just to figure out what goes in those blanks there, okay? So if I'm told that there are zeros of -2, 2, and I, that means x equals -2 is a 0. So how do I solve? I add 2 to both sides, and I get x plus 2 is equal to 0. That's one of my zeros. X plus 2 is a factor. Okay? If I know that 2 is a 0, then minus 2 on both sides. I get x minus 2 equal to 0. So x minus 2 is a factor. Oh man, we're doing pretty good now. And then I've given I. X equals I is a factor. So minus I. So I get x minus I equal to 0. That's a factor. But what about my last one? Well, what did I just get done teaching you, right? Imaginary solutions, imaginary zeros, have a conjugate pair. So if there's a plus, then there's a minus, right? So this one, we have x minus I. That means I also have an x plus I right there, okay? Now we're almost home. What other bit of information have we not used yet? We use this, that. Oh, we have f of 3 equals -150. -150. Okay. Look, right now, this is kind of annoying, okay? Why is it annoying? I have complex numbers and I have real numbers. So what I'm going to do is I'm going to multiply my complex things together. So FOIL, first, outer, inner, last, double distribute. X times x is x squared. X times I is xi. Negative x times I, okay, that's negative xi. Negative I times I, that's negative I squared. Now negative I squared is actually -1. So this is -1. So that's actually going to be 1. Okay? So, my goodness. Get your head turned around, right? And then these go to 0. So I really have x squared plus 1. So this when I multiply out gets me x squared plus 1. So let's summarize. F of x equals c times x plus 2 times x minus 2 times x squared plus 1. That's really nice because what you'll see is when I multiply conjugates together, I actually end up getting rid of the complex component. So really slick right there. So now when I plug in a 3 for f of x, everywhere I see an x, I put a 3. I'm going to get what? What am I going to get? I'm going to get c times 5 times 1 times 3 squared plus 1 is 10. So, and then f of 3 is equal to what? What does f of 3 equal? It equals negative 150. So negative 150. Okay, so negative 150 equals c times 50. So divide by 50, and c is negative 3. So my answer here, all right, f of x equals negative 3. Where'd the negative 3 come? That c right there, okay? Negative 3 times x plus 2, x minus 2 times x squared plus 1. Not bad. Not bad at all. All right? So you can leave it like this. I'm perfectly fine with that. If you want to multiply it out further, you could. If you multiplied this out, I'll let you do that, but you'll get x squared minus 4. And so I have x squared minus 4 times x squared plus 1, and then my minus 3. If I multiply this out, oh my goodness, I guess I'm going to get x to the 4th, and then minus 3x squared minus 4, and that'll multiply by negative 3, and that gets me negative 3x to the 4th plus 9x squared, and then plus 12. Okay? All right. Now, does this fit what we wanted? We wanted x to the 4th term. That tells me f is a degree 4. It's got the desired roots that we wanted. Man, this is really working out pretty nice. Okay? End of video.